In this module, we are going to learn multivariate functions too: expectations, covariance and correlation, linear combination of random variables. Just like we find mean, variance, covariance and correlation, in case of single variable, multivariate functions also have mean, which is the expected value, variance, covariance and coefficient of correlation. These variables may be correlated with each other, and their statistical dependence is often taken into account when analyzing such data. In fact, this consideration of statistical dependence makes multivariate analysis somewhat different in approach and considerably more complex than the corresponding univariate analysis when there is only one response variable under consideration. After studying this module, you shall be able to know the properties of expectation, know the properties of covariance and variance, know about coefficient of correlation, derive a linear combination of random variables. Let us begin our module with the discussion of expectations. Given any collection of k-dimensional random variables where y is equal to g bracket open x1, x2 right up to xk, it be a function of the k random variable and itself is a random variable. The expected value or mean of y is given by, in case of continuous random variables, ey is equal to integral sign minus infinity to plus infinity, again integral sign minus infinity to plus infinity, continues till minus infinity to plus infinity, where g bracket open x1 x2 up to xk is a function of bracket open x1 x2 to xk dx1 right up to dxk if the integral is defined, where function of x1 x2 to xk is the probability density function. In case of discrete random variables, Ey is equal to sigma x1, sigma x2, right up to sigma xk, g x1, x2 to xk, p x1, x2 to xk, where p x1, x2 to xk is the probability mass function. Now let us discuss properties of expectation. Expectation plays a vital role in statistics and many properties can be deducted from it. Depending on the random variable y, we can find out various statistics. Theorem 1. Let c be a constant. Then expected value of c is equal to c. Theorem 2. Let g x1 x2 be a function of the random variables x1 and x2 and let a be a constant. Then E bracket open a g x1 x2 bracket closed is equal to a expected value of g in brackets x1 x2. Theorem 3. Let x and y denote two random variables defined on the same probability space. Then E ax plus by is equal to a ex plus b ey. Theorem 4. Let x and y denote two random variables defined on the same probability space, and let g1 xy, g2 xy, and gk xy be functions of x and y. Then E g1 xy plus g2 xy plus gk xy is equal to E g1 xy plus E g2 xy plus continue till egkxy. Theorem 5. Let x1 and x2 be independent random variables and gx1 and hx2 be functions of x1 and x2 respectively. Then E gx1 hx2 is equal to E gx1 into E hx2 provided that the expectations exist. Coming on to covariance, the covariance between the two random variables x and y measures how much the two variables vary jointly, linearly in relation to one another. It represents the ratio of the standard deviation to the mean, and it is a useful statistic for comparing the degree of variation from one data series to another, even if the means are drastically different from each other. It is denoted by covariance xy or sigma xy. Covariance xy is equal to expected value bracket open x minus mu x into y minus mu y bracket close. Exy minus ex ey, which is equal to exy minus mu x mu y. Since x minus mu x and y minus mu y are the deviations of the two random variables from their respective mean values, therefore the covariance is the expected value of the product of deviations. Thus, with y equal to g x1 x2, which is equal to x minus mu x into y minus mu y, and now finding the expected value of y, that is Ey, will be equal to the covariance between x and y according to the definition of covariance. For discrete random variables xy, covariance xy is equal to sigma x sigma y x minus mu x into y minus mu y pxy. For continuous random variables xy, covariance xy is equal to integral sign minus infinity to plus infinity, again integral sign minus infinity to plus infinity, x minus mu x into y minus mu y function of xy dx dy, which can be derived easily. Let us discuss properties of covariance. For a positive relationship between x and y, the covariance should be positive, and for a negative relationship between x and y, the covariance should be negative. If x and y are independent, their covariance is 0. That is, x minus mu x into y minus mu y is equal to 0. Since x minus mu x into y minus mu y is equal to exy minus ex ey is equal to ex ey minus ex ey, which is equal to 0. However, the converse of this theorem need not necessarily hold. That is, it is possible for two variables to have a covariance of 0 and yet be non-linearly related. A zero covariance only implies the absence of a linear relationship between two variables. The covariance between the same random variable is the variance of its random variable. Covariance xx is equal to x minus mu x into x minus mu x bracket close, which is equal to x minus mu x the whole square, which is equal to vx. Example, the joint and marginal PMFs for X, which is equal to automobile policy deductible amount, and Y, which is equal to homeowners policy deductible amount, were X is equal to 10, 25 and Y equal to 0, 10, 20. From the information we have, from this we can find out the marginal distributions of X and Y. Table is derived by adding all the probabilities over y for a given fixed capital X is equal to small x. That is, for given x is equal to 10, we add for y, which is equal to 0, 10, 20. That is, p y equal to 0 plus p y equal to 10 plus p y equal to 20, which is equal to 0.20 plus 0.10 plus 0.20, which is equal to 0.50. Similarly, for x equal to 25, we add for y equal to 0, 10, 20. That is, p y is equal to 0 plus p y equal to 10 plus p y equal to 20, which is equal to 0.05 plus 0.15 plus 0.30, which is equal to 0.5. In a similar manner, we can make a table for the marginal distribution of y. From previous tables, we can find out the expected value of x and y. Ex is equal to mu x, which is equal to sigma x px of x, which is equal to 10 multiplied by 0.5 plus 25 multiplied by 0.5, which is equal to 17.5. Ey is equal to mu y, which is equal to sigma y py of y, which is equal to 0 into 0.25 plus 10 into 0.25 plus 20 into 0.5, which is equal to 12.5. We can calculate the value of covariance for two random discrete variables by the given formula. Covariance xy is equal to sigma x sigma y bracket open x minus 17.5 into bracket open y minus 12.5 p xy. which is equal to 10 minus 17.5 into 0 minus 12.5 into 0.20 plus, which continues till 25 minus 17.5 into 20 minus 12.5 into zero point 0.3, which is equal to 18.75. Now we will move on to correlation. The correlation coefficient, which is indicated by the symbol rho, which is in Greek called the Greek rho, gives a measure of the extent to which the random variables x and y are linearly related. It represents the ratio of the standard deviation to the mean, and it is a useful statistic for comparing the degree of variation from one data series to another, even if the means are drastically different from each other. The basic difference between covariance and correlation coefficient is that covariance is an absolute measure which depends on the units in which x and y are measured, whereas correlation coefficient is a relative measure free from the units of measurement and is thus more useful in comparative purposes. Rho is equal to sigma xy by sigma x sigma y, where sigma x is standard deviation of x, which is equal to under root vx, and sigma y is equal to standard deviation of y, which is equal to under root vy. Next, we will discuss properties of correlation. It always lies between -1 and +1 inclusive. That is, r is greater than equal to -1 and 1 is greater than equal to r. Since the absolute values of the two random variables cannot exceed the product of their standard deviation. Thus, if rho is equal to 1, it indicates perfect positive correlation. If rho lies between 1 and 0, it indicates positive correlation. That is, when one variable increases or decreases, the other will also increase or decrease. If rho is equal to 0, it indicates no correlation, but the covariance is 0. If rho lies between 0 and -1, it indicates negative correlation. That is, when one variable increases or decreases, the other will correspondingly decrease or increase. This implies that the two random variables will move in the opposite direction. If rho is equal to -1, it indicates perfect negative correlation. If there is a perfect linear relationship between x and y, that is, if ax plus by plus c is equal to 0, then rho of xy is equal to +1 if a is greater than 0 and -1 if 0 is greater than a. Next, we will discuss properties of correlation. The correlation coefficient is not affected by the change of origin and scale. That is, if we change the origin or scale or both, the value of the new correlation coefficient will remain unchanged. R bracket open ax plus b comma cy plus d is equal to rxy. The coefficient of correlation between two independent variables is always 0, but the converse need not always be true. That is, if the coefficient of correlation is 0, then it is not necessary that the two variables are independent. This is because they can be non-linearly correlated. The sign of the correlation coefficient is the same as the sign of the covariance. This implies that if the covariance is positive, then the value of correlation coefficient lies between 0 and +1. And if the covariance is negative, then the value of the correlation coefficient lies between 0 and -1. From the example of automobile policy deductible amount and homeowners policy deductible amount, it is easily verified that Ex squared is equal to sigma x squared pxx, which is equal to 10 squared multiplied by 0.5 plus 25 squared multiplied by 0.5, which is equal to 362.5. Hence, sigma squared x is equal to Ex squared minus Ex the whole squared, which is equal to 362.5 minus 17.5 the whole square, which is equal to 362.5 minus 306.25, which is equal to 56.25. Therefore, sigma x is equal to 7.5. Similarly, for y, we have Ey squared is equal to sigma y squared pyy, which is equal to 0 squared into 0.25 plus 10 squared into 0.25 multiplied by 20 squared into 0.5, which is equal to 225. Hence, sigma squared y is equal to Ey squared minus Ey the whole squared, which is equal to 225 minus 12.5 the whole squared, which is equal to 68.75. Therefore, sigma y is equal to 8.292. Given covariance xy, which is equal to 18.75, sigma x is equal to 7.5 and sigma y is equal to 8.292. We can now find the value of correlation coefficient. Sigma xy is equal to 18.75 divided by 7.5 multiplied by 8.292, which is equal to 0.301 approximately. Finally, we will discuss linear combination of random variables. Linear combination of random variables often deals with random variables which are related to other random variables by some specified mathematical function. For instance, a random variable y may be defined as a constant times another variable x, or a random variable k may be defined as being equal to the sum of two random variables m and n, etc. Given a collection of n random variables x1 to xn and n numerical constant a1 to an, the random variable y is equal to a1 x1 plus continue to an xn is equal to sigma I from 1 to n ai xi is called the linear combination of xi's. Theorem. Let x1, x2 to xn have a mean value of mu1 to mun respectively and variances sigma 1 squared to sigma n squared respectively. Then first, whether or not the xi's are independent, E bracket open a1 x1 plus a2 x2 continue to an xn is equal to a1 ex1 plus a2 ex2 plus continue to an exn is equal to a1 mu1, which continues to an mu n. V bracket open a1 x1 continues to an xn bracket close is equal to sigma I from 1 to n into sigma j from 1 to n ai aj covariance xi xj. That is, the covariance between any pair of independent variable is 0. 2. If x1 to xn are independent, then the previous formula of variance reduces to v bracket open a1 x1 plus a2 x2 continues to an xn bracket close is equal to a1 squared vx1 plus a2 squared vx2, which continues to an squared vxn, which is equal to a1 squared sigma 1 squared plus continuing to an squared sigma n squared, since sigma I is equal to 1 to n into sigma j is equal to 1 to n ai aj covariance xi xj is equal to 0 for I not equal to j. Proposition. In case when we have only two random variables with their coefficients being 1 and minus 1, that is n is equal to 2, a1 is equal to 1, a2 is equal to minus 1, then y is equal to a1 x1 minus a2 x2, which is equal to x1 minus x2. Corollary to the previous proposition. E x1 minus x2 is equal to ex1 minus ex2 for any two random variables x1 and x2. Vx1 minus x2 is equal to vx1 plus vx2 if x1 and x2 are independent random variables. Thus, the expected value of a difference is the difference of the two expected values, that is, ex1 minus x2 is equal to ex1 minus ex2. But the variance of a difference between two independent variables is the sum, not the difference of two variances. That is, vx1 minus x2 is equal to vx1 plus vx2. This means that there is just as much as variability in x1 minus x2 as in x1 plus x2. In bracket, writing x1 minus x2 is equal to x1 plus bracket open minus 1 x2, which implies that minus 1 x2 has the same amount of variability as x2 itself. Also, if the independent variables are themselves normally distributed, a linear combination of them will be normally distributed with mean and variance. For example, the weekly wages of a firm's employee X are normally distributed about a mean of $200 with a standard deviation of $10. If all the employees of the firm were awarded a wage increase of 15%, what would be the mean and standard deviation of the new distribution of employees' wages? B, if all employees, instead of being awarded a wage increase of 10%, received a flat $14 increase per week, what is now the mean and standard deviation of the new distribution of employees' wages? Solution. Let Y denote the weekly wages earned by the employees after the rise. With C is equal to 1.15, mu X is equal to 200, sigma X is equal to 10. Mu Y is equal to A mu X, which is equal to 1.15 multiplied by 200, which is equal to 250, and sigma Y squared is equal to A squared sigma X squared, which is equal to 1.15 the whole squared into 10 the whole squared. Therefore, sigma Y is equal to 1.15 into 10, which is equal to 11.5. The new variable Y will also be distributed normally with a mean of $230 and standard deviation of $11.5. Over here, the new variable Y is equal to C plus X, where C is equal to 14. Hence, mu Y is equal to C plus mu X, which is equal to 14 plus 200, which is equal to 214. Since variance Y is equal to variance C plus X, which is equal to variance X. Adding a constant to every possible observation of a random variable leaves the variance unchanged. Therefore, sigma Y is equal to sigma X, which is equal to 10. That is, granting a flat $14 increase in wages increases the mean by the same amount but leaves the variance and standard deviation unchanged. Now let us summarize what we have learnt in this module. The expected value of a discrete or a continuous random variable is the sum or integral of that variable with respect to its probability measure. The covariance is a standardized measure of dispersion of probability distribution or frequency distribution and measures the linear relationship between them. A correlation coefficient is a statistical measure of the degree to which changes to the value of one variable predict change to the value of another. Given a collection of n random variables x1 to xn and n numerical constant a1 to an, the random variable y is equal to a1 x1 plus a2 x2 right up to an xn, which is equal to summation I from 1 to n ai xi, is called the linear combination of the xi's prime